In this video, we are going to look at Atwood's machine. Hi, this is Sean Huang from the Physics Department. If you have not watched the video on examples of Newton's laws, you can find the link down below in the description. This is Atwood's machine, which consists of a pulley, a cord, and two masses tied to the two ends of the cord. The pulley has negligible mass, as does the cord. We can assume that M2 is bigger than M1, so that M2 will move downward and M1 will move upward. The two masses will move in sync. The question is, what will be the acceleration of either of the two masses? The problem will be easy if you realize that Newton's second law can be applied to only one mass at a time. So we'll divide the problem into two parts. Cut it right in the middle, neglecting the pulley altogether. On the left, you have a mass moving up with an acceleration a because of the tension in the cord. This problem is exactly the same as the rescue helicopter problem. In other words, problem number 61 of chapter 4, which is solved in the video referenced earlier. The part on the right is similar, except that the mass moves in the opposite direction. In the following, we will solve the problem from scratch. In each of the two parts, we will choose the forward direction as the positive going direction. According to Newton's second law, the product of mass and acceleration will have to be equal to a net force. Since m1 is moving up, we can assume that T is greater than the gravitational force m1g. So we have T minus m1g equals to m1a. On the right, since m2 is moving down, we can assume that the gravitational force m2g is greater than T, so that we have m2g minus T equals to m2a. Now, since the cord is tight, the tension in the cord is everywhere the same, so the two T's in the two equations are the same. We then have a set of two simultaneous equations. We can add the two equations together, eliminate T, and solve for A. We can then plug A back into the first equation to solve for T. Notice that there isn't a single coordinate system that will work. Further, in each of the two parts, we have to choose a coordinate system that best suits the situation. And that completes our treatment of Atwood's machine.